So I want you to pick up your phone right now. Just open your favorite app. You know, the one you use every single day without even thinking about it.
Well, we all have one.
Right, and just look at it. Look at the fluid animations, the deep layered glass effects, those, beautifully sculpted buttons that they seem to invite your thumb to press them.
They look real, like physical objects.
Exactly. But what if I told you that none of it actually exists? Like, at all. It is a massive real-time illusion.
It really is.
Your device is essentially, it's just a high-powered calculator, right? Doing rapid-fire geometry. It's shifting these invisible, mathematically defined rectangles around millions of times a second just to trick your visual cortex.
Yeah, it is basically the ultimate sleight of hand. We look at a digital interface and we see this tactile living environment, right? We see materials and lighting and physical hierarchy.
Mm-hmm.
But under the hood, the entire architecture of the digital world, it relies on this remarkably rigid, almost brutalist foundation of basic mathematics.
Which honestly brings us to the core mission of today's deep dive. We are tearing down that illusion.
Let's do it.
Yeah, for anyone listening who is, building a career in tech or designing products or just wants to understand the matrix behind that glass screen in your pocket, we are taking a sledgehammer to the glossy exterior today.
I love that, breaking it down to the studs.
Exactly. And we're pulling our framework today directly from an incredibly practical source. It's Chapter 09, Objects, from the book Design User Interface.
It's great text.
It really is. It's this foundational text that just strips digital design down to its rawest mechanics. And for you listening, I want to make sure you get this. So the book is Design User Interface, and you can find it at hype4academy.gumroad.com/L/ubook. That's HRYPE, the number 4 academy.gumroad.com/L/ubook.
Highly recommend picking it up.
Absolutely. And you can buy the book right now just by scanning the QR code of the book link that we provided in the description below. Super easy. And hey, while you're down there, make sure you follow us for more technical design breakdowns and career building content, because we do this all the time.
We do. And, the value of this specific chapter is its total refusal to romanticize the design process.
Right. No fluff.
Zero fluff. It totally bypasses the abstract philosophy of aesthetics and it immediately zeroes in on the literal mechanics of how rendering engines and layout tools actually construct the interface that you interact with.
Okay, let's unpack this, because the text hits you with a claim right out of the gate that sounds almost absurdly reductive.
Oh, I know the one you mean.
Yeah, it states, and I quote, "UI design is moving rectangles around."
Yep, there it is.
At first glance, that feels almost like an insult to the profession, doesn't it?
It sounds like telling an architect that their job is just stacking bricks.
Right, but if you look at how digital layout engines actually process information, it's not a metaphor at all. It is the literal truth of the medium.
It is the atomic theory of digital design, basically. To understand why the rectangle dominates everything we do, we kind of have to look at the divergence between how human beings traditionally create art versus how a computer renders a graphic.
Okay, break that down for me.
So most people implicitly understand raster graphics. Like, that's the technology behind digital photography.
Right, JPEGs, PNGs, that sort of thing.
Exactly. A raster image is just a finite grid of pixels, where each tiny square is assigned a specific color value.
Right, so if you take a photograph and zoom in like 500%, the illusion just breaks.
Completely shattered.
You stop seeing a face and you start seeing a mosaic of hard-edged, colored tiles, because the computer is just holding a static map of those tiles, right?
Yes, exactly. It's finite data.
Yeah.
If you try to stretch a raster image to the size of, say, a highway billboard, the software has to guess what to put in the new gaps.
Which is why it degrades into that awful, blurry, pixelated mess.
Right. But exactly the opposite is true for the objects that make up a user interface. UI relies on vector graphics.
Okay, and a vector is not a grid of pixels.
No, not at all. It is a mathematical equation. When a designer creates a button with a curved edge, they aren't painting pixels on a canvas. They're establishing a coordinate, plotting a Bezier curve, and basically defining a mathematical relationship between points.
It's kind of like a recipe, right? Like, instead of baking a cake of a fixed size, which would be your pixel image, a vector is the recipe itself.
Oh, I like that analogy.
So, using that recipe, you can bake a tiny cupcake or a massive wedding cake, and it has perfect proportions every single time.
That's a perfect way to look at it. Because it's pure math, The rendering engine can recalculate that formula on the fly, whether it's outputting to a tiny smartwatch screen on your wrist or a massive 8K stadium display.
And the sharpness never degrades because the math simply recalculates for the new scale.
Exactly. And, the history here is actually fascinating. The Bezier curve, which is the whole foundation of modern vector design.
Yeah.
It was popularized in the 1960s by Pierre Bezier, who was an engineer at Renault, the car company.
Wait, really? A car company invented UI curves?
Basically, yeah. He needed a mathematical way to ensure that the physical curves of car bodies could be modeled precisely and scaled up for manufacturing without losing their smooth aerodynamic properties.
Oh, wow.
Yeah, so that exact same automotive engineering math is what allows your Instagram app icon to scale infinitely today.
That is wild. But, the text notes a really specific quirk about this mathematical landscape because despite having the power to draw any sweeping, complex curve imaginable like a car door, the fundamental building block of UI design is almost exclusively the rectangle.
Yeah, the humble rectangle.
Even ellipses, like circles and ovals, the book says they're a distant second. So if we have the mathematical power to build interfaces out of, hexagons or organic blobs or triangles, why does the entire digital ecosystem default to a rigid box?
Well, it really comes down to a convergence of hardware limitations and human cognitive processing.
Okay, let's start with the hardware side.
Sure. So first, consider the physical matrix of the screen you are looking at right now. Every modern display is a rectangular grid composed of millions of rectangular subpixels.
Right.
Computationally speaking, drawing a straight horizontal or vertical line along that grid requires significantly less processing power than calculating the anti-aliasing, the smoothing effect required to draw a diagonal line or complex curve.
Oh, that makes total sense from a rendering perspective. I mean, if a phone screen refreshes 120 times a second, forcing the GPU to calculate complex organic boundaries for every single interactive element,
It would be a nightmare.
yeah, a massive unnecessary drain on the battery and the processing power. So rectangles are just computationally cheap.
Yeah. They are very cheap. And they are incredibly efficient for packing algorithms. Like, think about how a layout engine like CSS Flexbox or CSS Grid operates on a website.
Okay.
It calculates the available viewport space and divides it up, trying to calculate the collision detection and spatial relationships of, say, 100 overlapping circles. That is incredibly difficult math.
But rectangles just slot together perfectly, like Tetris.
Exactly like Tetris. But it's not just the hardware, The rectangle dominates because of how the human visual cortex processes structured information.
You mean how we read? Because we
Yeah.
are conditioned by thousands of years of reading physical texts, right? Books, scrolls.
Yes. The Gutenberg diagram, the F pattern of eye scanning, we naturally seek out block-like structures of information. Text naturally flows in rectangular blocks.
So when we look at a complex interface, let's say a dashboard on Airbnb or Spotify, we don't see a chaotic jumble of data.
No, our brains immediately parse the screen into a hierarchy of cards, lists, and navigation bars.
Right. If you take a screenshot of any major application right now and draw red lines around every distinct piece of content, you will end up with this intricately nested grid of rectangles.
Exactly, which means that the advice from Chapter 09 to view UI design simply as moving rectangles around, it isn't just a simplification for beginners.
It's the reality.
It is a necessary cognitive shift for anyone trying to build digital products. You really have to stop thinking like a fine artist painting a canvas and start thinking like a systems architect defining spatial volumes.
I love that. Architect of space. And if every element on a screen is fundamentally a rectangle, we really need to understand the anatomy of how the layout engine interprets that space, which leads us directly to the box model.
Yes. The box model. It is the Rosetta Stone of digital layout.
It really is.
It is the shared conceptual framework that bridges the gap between the visual designer who's manipulating shapes in a tool like Figma and the front-end engineer who's writing the code to actually deploy it.
Right.
If you do not internalize the box model, you cannot build a functional interface, period.
So the text breaks this model down into 4 distinct anatomical parts. Let's deconstruct them, and not just as visual layers, but as the invisible forces that dictate how elements behave when they are pushed together on a screen.
Sounds good.
The first layer is straightforward. It's the object itself. This is the core content. So the text of a button, an icon, or a photographic image.
The nucleus.
Right. But the tension really begins with the second element, which the text calls the inner margin, commonly known as padding.
Yes, padding. Padding is best understood as internal pressure. The text defines it as the safe area inside the object between the core content and the boundary line. But structurally, padding is what gives an object its physical mass.
Let's apply that. I want to use a real estate analogy here. Let's say the object is your house, right? The actual building you live in.
Okay.
The inner margin, the padding, is the empty space inside your house. It's the space between your furniture and your wall.
I like it.
If I create a button that just says submit and I apply 0 padding, the clickable boundary of that button tightly hugs the typography. It feels suffocated, like a house packed floor to ceiling with boxes.
Right, very claustrophobic.
But if I increase the padding, I am pumping invisible pressure into the box. The boundary walls expand outward away from the text, creating breathing room. It doesn't change the size of the font at all, it just changes the spatial volume of the container holding the font.
Precisely. And this internal volume is critical for usability. Especially on touch interfaces.
Yeah.
Like Apple's human interface guidelines dictate a minimum hit target of 44 by 44 points for any interactive element on a phone screen.
Right, because of our clumsy fingers.
Exactly. The word submit might only be 15 points high. The padding is the invisible dark matter that expands the mathematical footprint of that button, so a human thumb can comfortably tap it without accidentally triggering the element next to it.
Okay, so padding expands the box outward from the inside. Now the third element is the border. In our real estate analogy, the border is your physical fence around the property.
Right, the perimeter wall effect.
Exactly. It wraps around the outer edge of that padded space. Now, we will dissect the granular math of borders a bit later, but for now, we can just think of it as the skin of the box. Which brings us to the fourth element, the outer margin, or simply just margin.
Right.
If padding is internal pressure, margin acts as an external repelling force. It's your front yard, keeping your neighbors at a safe distance.
That is an excellent way to conceptualize it. Margin is the invisible magnetic field generated by the object. It dictates the minimum safe distance between the object's border and anything else on the screen.
So let's say I have 2 cards stacked vertically on a page and they look way too crowded. I don't increase the padding, right?
No, definitely not.
Because if I increase the padding, the cards themselves just get larger, but their borders are still touching each other. They're just bigger and still crammed together.
Right. What you have to do is increase the margin on the bottom of the first card,
Okay.
which essentially projects an invisible force field downward, pushing the second card away and creating structural white space.
Okay, that makes perfect sense. The mastery of UI layout, then, is basically entirely about managing the tension between padding and margin.
It really is. But there is a crucial counterintuitive rule within the box model that trips up almost every beginner.
Oh yeah, the bounding box.
Yes. What's fascinating here is how the source material emphasizes this explicitly. It says, the width and height are always of the smallest possible rectangular box that can contain our object, even if the object itself has an irregular shape.
Right. This concept is huge. Let's say I draw a perfect smooth circle in a design tool. My human eye sees a continuous organic curve, but the layout engine, it doesn't see a circle.
No, it sees a square. It calculates a rigid, invisible square that acts as a cage, perfectly enclosing the absolute outermost points of that curve.
It's kind of wild to think about.
This goes back to our earlier discussion on computational efficiency,
Yeah.
Let's say you have a 5-pointed star icon, and you want to align it to the left edge of a text block. If the software had to calculate the alignment based on the complex geometry of the star's points and all its indentations, the rendering math becomes exponentially more complex.
Right, because which point of the star is the edge?
Exactly. But by wrapping the star in a rigid bounding box, a mathematical container defined by the absolute highest, lowest, furthest left, and furthest right points of the star alignment becomes a trivial calculation.
You're just matching the x-coordinate of the invisible box to the text block.
Yep, it's a system of abstraction. The software is basically keeping 2 sets of books.
Like an accountant.
Yeah, exactly. It maintains the raw vector path data to draw the star visually for you to see, but for the physics engine of the layout for collision detection, spacing, and alignment, it only interacts with the invisible rectangular cage. It forces everything back into the paradigm of moving rectangles around.
Man, it really solidifies the core concept. Okay, so once we establish that everything is a rigid box, the layout engine needs a universal system to determine exactly where to drop those boxes on the screen.
Right, and that requires a coordinate plane.
Right. And the source material dives into position and angle next, noting that position is defined by x and y coordinates on the artboard. Now, anyone who has taken basic geometry in high school understands a Cartesian plane, right? X is horizontal, y is vertical.
Sure.
But the implementation of coordinates in UI design tools has a really specific historical quirk, because in traditional math, the origin point 0, 0 is in the bottom left corner. As y increases, you move up.
Right.
But in almost all UI design software, 0, 0 is anchored to the absolute top left corner. As y increases, the object moves down the screen. Why did the tech industry invert the mathematical standard? It seems so backward.
It really does seem backward, but it is a relic of hardware architecture. Specifically, it's the way early cathode ray tube, or CRT, monitors functioned.
Oh, the big heavy monitors from the 90s.
Exactly. A CRT monitor drew an image on the screen by firing an electron beam magnetically back and forth across a phosphor-coated glass tube.
Like a typewriter scanning across a page.
That's a great analogy. The beam always started in the extreme top left corner of the screen. It scanned horizontally across a single line, then snapped back, moved down a fraction of a millimeter, and scanned the next line, all the way down to the bottom right.
Wait, so the coordinate system of modern digital design, the tools we use to design iPhone apps today, is permanently tethered to the physical scanning trajectory of an electron gun from the 1970s.
It is. The hardware dictated the rendering engine's logic. 0 on the x-axis and 0 on the y-axis represented the exact microsecond the electron beam began its sweep. Decades later, we design on OLED matrices that don't use electron beams at all, but the underlying mathematical architecture of the coordinate system remains completely unchanged. Top left is absolute 0.
That is just incredible. Okay, so we pin our bounding boxes to this top left origin using x and y, but we also have to deal with rotation, which the text refers to as angle. The default state is 0 degrees. And here the text offers a really fascinating warning. It explicitly states, if we want to have a consistent interface, it's best not to rotate objects by hand, but instead enter the right angle from the keyboard, as it is way more precise.
Yeah, this touches on a subtle but really profound psychological aspect of user experience.
Okay, how so?
Well, the human visual system is incredibly sensitive to minute inconsistencies, even if the conscious mind doesn't actually register them.
Right.
Let's say a designer is creating an interface with a scattering of Polaroid-style photos. If they grab the corner of each photo with their mouse and manually twist it, the resulting rotation values will be chaotic. You'll have one at 13.7 degrees, another at -8.2 degrees, another at 15.1 degrees.
I mean, I assume the layout engine has no problem rendering those fractions, right?
Well, the engine doesn't care at all. It calculates the matrix transformation flawlessly. The problem is the human user looking at the screen. When an interface relies on arbitrary fractional numbers, it subconsciously feels unpolished. It introduces cognitive friction.
Oh, interesting.
Yeah, professional UI design is about establishing mathematical rhythms. Typing in deliberate whole number angles, say 10 degrees, -5 degrees, 15 degrees, it creates a hidden structural logic. The user perceives the interface as robust, engineered, and intentional rather than messy.
It's the difference between tossing tools into a drawer randomly versus placing them into those custom-cut foam inserts, right?
Exactly.
The mathematical precision is invisible, but the feeling of order is absolutely palpable. And wait, the book also points out a math quirk here that I love. -15 degrees and 345 degrees are the exact same thing to the software.
Right, because it's just a circle. It's just a different way of inputting the same geometric truth.
Now, there is an operation mentioned in the text related to rotation called flattening.
Ah, yes.
And the source gives a stern warning here. It says, if we flatten the object, it resets the angle to 0, but it is still rotated. Only the new perspective becomes the base for further rotation. Flattening also converts rounded corners into a rounded path, so only do it if you really have to.
It's a very important warning.
Let's unpack the mechanics of flattening. What is the software actually doing to the vector data when you click flatten? Why would someone ever want to do it if it ruins their ability to edit it later?
To understand flattening, you really have to understand non-destructive versus destructive editing.
Okay.
When you draw a square and apply a 45-degree rotation in the property panel, the software is practicing non-destructive abstraction. The raw data of that object is still a perfect, unrotated square. The software is just applying a real-time mathematical filter, a rotation matrix over it, right before it renders to the screen.
So the software remembers the original state. If I change the rotation value back to 0, it instantly snaps back to a flat square because the core geometry was never actually altered.
Correct. Furthermore, because it remembers it is a square, it retains parametric control over things like border radius. It knows how to calculate the curve of a corner on a standard rectangle. But when you select that rotated square and execute a flatten command, you are forcing a destructive operation. You are telling the software, throw away the history, take the current visual state, this diamond shape currently being generated by the rotation matrix, and bake those exact absolute pixel coordinates into a brand new raw vector path.
It's like baking the cake. You can't unbake it back into flour and eggs.
Exactly.
So the moment I flatten it, the rotation property resets to 0. Because to the software, it's no longer a square rotated 45 degrees. It is now fundamentally a diamond sitting at its natural 0-degree state.
Yes, and that is exactly where the danger lies. By baking the transformation into the raw path data, you destroy all those parametric properties. If you had rounded corners on that square, they're no longer mathematical border radiuses that can be easily adjusted in a property panel.
They're just fixed curves now.
Right. They're permanently converted into fixed Bezier curves. If a client later asks you to reduce the roundness of the corners by 2 pixels, you can't just type a new number into a box. You have to manually drag individual vector anchor points around, which is tedious, error-prone, and totally destroys the mathematical precision of your layout.
So flattening's a one-way trip.
Yes. You only do it when you absolutely must merge complex paths together, like creating a custom logo icon, never as a casual part of daily layout manipulation.
Good to know. Okay, so we've established the rigid mathematical framework of the box model and the coordinate plane. But, a wireframe of sharp rectangles doesn't give us an interface that feels human.
No, it feels like a spreadsheet.
Right. To hack the user's perception and create something inviting, we have to manipulate the geometry and simulate physical materials. And here's where it gets really interesting. The source material dives deeply into this under what I would call the psychology of geometry, starting with border radius.
Border radius is fascinating because it's a seemingly minor parameter, usually just a single number dictating the curve of a corner, but it carries an immense amount of psychological weight.
The text notes that border radius is measured in points and then makes a crucial observation. It says, in general, even slightly rounded corners, between 2p and 6p, are considered more friendly than sharp ones of 0p.
Yeah, it is remarkable that changing 4 pixels of math can completely alter the emotional resonance of a software application.
Think about it. A button with a 0-point border radius, perfectly sharp 90-degree corners. It feels authoritative, rigid, almost aggressive. It demands interaction rather than inviting it.
Well, this is actually a direct response of the human amygdala, which is hardwired by evolutionary biology to rapidly assess threats.
Oh, caveman brain.
Exactly. In the natural, physical world, perfectly sharp, 90-degree right angles are exceedingly rare. When they do occur, they usually signify danger. Like a jagged rock, a broken branch, a sharp edge. The brain subconsciously processes a sharp corner as an object that requires careful handling to avoid physical injury.
Wow. So when a user is navigating an interface full of sharp, brutalist rectangles, their visual cortex is constantly processing microfriction. It feels like navigating a room full of glass coffee tables. You are subconsciously braced for impact.
That's a brilliant way to put it. You're braced for impact. But the moment you apply a tiny border radius, just 4 points of curvature, you completely disarm the threat response.
Because you simulate the physics of a physical object that has been machined, tumbled, or worn smooth, it implies safety, like a pebble.
Right. The user instinctively feels that the interface is tactile and welcoming. However, the source material introduces a critical constraint to this rule.
Right, you can't just use any random number.
No. It warns that border radius cannot be arbitrary. It states, it's good to have consistency in the roundness. The grid base unit that we select should define the border radius. It should also match its surroundings.
The grid base unit. Okay, in modern digital design, almost everyone relies on an 8-point spatial grid. Spacing, typography line heights, margins are all calculated in multiples of 8, so 8, 16, 24, 32. Why did the industry standardize on the number 8, and how does that dictate our border radius?
The 8-point grid is basically a mathematical necessity born from screen pixel densities.
Okay, explain that.
So early smartphones had a 1-to-1 ratio of software points to hardware pixels. 1 point in Figma equaled 1 tiny light bulb on the screen. But as Retina displays evolved, screens packed more physical pixels into the exact same physical space. A single software point might be rendered by a 2x2 grid of hardware pixels, or even a 3x3 grid.
Okay, so if you design an element that is 5 points wide and it needs to render on a 2x retina screen, it takes up 10 pixels. That's clean math.
Exactly. But what if it renders on a 1.5x screen? You get 7.5 pixels.
And you can't light up half a physical pixel on a monitor.
No, you can't. The rendering engine has to blur the edge to compensate a process called anti-aliasing, which makes the interface look fuzzy and soft.
Ah, so the number 8 is a powerhouse because it is highly divisible.
Yes. You can divide 8 by 2 and by 2 again and still get clean, whole numbers. By basing all spatial dimensions on multiples of 8, you guarantee that elements will scale crisply across the totally chaotic fragmentation of different device screen densities.
So when the text says the border radius should match the base unit, it means you shouldn't use a random curve like 7 points or 11 points. If your layout is built on an 8-point rhythm, a border radius of 4 8 points harmonizes with the underlying math of the interface.
It creates a subliminal rhythm. Every dimension is singing in the exact same mathematical key.
Okay, so now the text moves from the corners of the box to the perimeter wall itself. Borders. And it highlights a granular mathematical trap here that I guarantee has ruined thousands of beginner layouts.
Oh, absolutely.
It describes 3 distinct ways the software can render a border: inner, centered, and outer. It gives an example of a 60-point square with a 2-point border. Walk me through the physical footprint of these 3 options.
Sure. This is a classic conflict between visual perception and layout engine mechanics. You have your bounding box, which dictates the space the object claims on the screen. Let's say it is exactly 60 by 60 points.
Okay, 60 by 60.
If you apply a 2-point inner border, the rendering engine draws that 2-point line entirely inside the bounding box. The line eats into the padding space. But crucially, the external physical footprint of the object remains exactly 60 by 60. The math of your grid is completely undisturbed.
Okay, the inner border respects the boundaries. What about a centered border?
A centered border straddles the mathematical boundary line. It puts 1 point of thickness inside the box and 1 point of thickness outside the box. So your 60-point square is now visually taking up 62 points of space on the screen.
And the outer border?
The outer border pushes the entire 2-point stroke outside the boundary line, meaning the object now consumes 64 by 64 points of layout space.
Right, and here is why this is so dangerous. In many design tools, if you apply an outer border, the property inspector panel will still tell you the object's width is 60 points.
Yes, it is reporting the size of the base vector path and ignoring the expanded footprint created by the border stroke.
That is devious. So a designer builds a meticulously calculated 8-point grid. They space a row of cards exactly 16 points apart. Everything looks great. Then they decide the cards look a bit flat, so they throw a 2-point outer border on them to make them pop.
And suddenly, their mathematically perfect 16-point gap is visually reduced to 12 points, because the outer borders are secretly bleeding into the margin space.
The layout feels cramped, the grid is broken, and the designer has no idea why, because the property panel is literally lying to them.
Exactly. This is why in front-end development, there was a massive paradigm shift years ago when CSS introduced the box sizing border box property.
Oh, I've heard of that.
Yeah, it forced the browser rendering engine to push borders and padding inward, rather than allowing them to expand the element outward, which completely stabilized layout math. Modern UI design tools have adopted this logic, which is why inner borders are the overwhelmingly preferred standard for beginners.
Because they guarantee that an object will never violate the spatial constraints you have assigned to it.
Exactly.
Okay, so we have defined our boundaries, we have safely rounded our corners, and we have applied our inner borders. The container is perfect, but a wireframe doesn't hold a user's attention. We have to give the object mass, color, and make it interact with light.
Right, it needs to look like a real physical object the user wants to touch.
Exactly. The text tackles this in its section on fills and shadows. It starts by noting that fills aren't just single colors. They can be gradients, photos, and crucially, they can be stacked.
Stacking fills is a game changer.
The example it gives is adding a transparent color to a photo will colorize the result so it can match the rest of your UI.
The ability to stack fills is an incredibly powerful non-destructive technique. It relies on matrix math and algorithmic blending modes.
Give me a practical example.
Let's say you have a hero section in an app with a photograph of a bustling cafe. The photo is rich in warm tones, lots of yellows, reds, browns, but your application's brand identity is built on a cool, stark navy blue.
Right. If you just place the warm photo in the layout, it creates a jarring visual disconnect. It looks like it belongs to a different company.
Exactly. Now, in the old days, you would have to take that photo into an external raster editor like Photoshop, apply a blue color filter, permanently save the new pixels, and re-import it into your layout.
Which is a destructive workflow, because what if you want to change the shade of blue later?
You'd have to do the whole process over again. But in modern UI software, the bounding box of that hero section acts as a layered matrix. The bottom fill layer is the raw photograph. You then add a second fill layer directly on top of it within the exact same object, a solid navy blue.
Okay.
But you reduce the opacity of that blue layer to, say, 60%.
So the software's rendering engine takes the RGB values of the pixel in the photo, runs an algorithm against the RGB values of the semi-transparent blue layer above it, and outputs a newly calculated tinted pixel to the screen in real time.
Yes. It acts as a dynamic color gel, like in theater lighting. It homogenizes the visual tone of the photography to match the UI environment, and because it is mathematically calculated on the fly, you can adjust the opacity or swap the base photo instantly without ever leaving the layout tool.
That is so slick. It makes the object feel like it belongs in the environment. But color alone doesn't create depth. To convince the human brain that this glowing glass screen actually contains a dimensional space, designers rely on simulating the physics of light.
Shadows.
The source material delivers what might be the most critical piece of aesthetic advice in the entire text regarding drop shadows.
I know exactly what you're going to say.
It states, the most important part of looking natural is avoiding pure black shadows and using a shadow derived from our primary color instead.
Golden rule of UI right there.
Yep. Y is a pure black shadow hex code 000000, so universally recognized as amateur design. Why does our brain reject it instantly even if we can't articulate why?
If we connect this to the bigger picture, it fundamentally violates the physics of how light operates in the real world.
Okay, science time.
In a physical environment, light is rarely emitted from a single isolated point source. We are constantly surrounded by ambient occlusion. Light particles, photons, are emitted from a source, hit a surface, and bounce. When they bounce, they carry the color data of the surface they just struck.
So if I have a solid green button sitting on a white background, the light hitting the green button is bouncing off of it, carrying green color data into the surrounding space.
Yes. Furthermore, a shadow isn't an object itself. It is simply an area where direct light is occluded, or blocked. But that occluded area is still being bombarded by bounced ambient light from the room and from the object itself.
Oh, therefore, a shadow cast by a green object onto a white surface in a lit room will never ever be pure black.
Never. It will be a deeply desaturated dark green.
So when a designer uses a pure black shadow on a digital screen, they are telling the visual cortex that the object exists in a complete vacuum, devoid of all ambient bounced light.
Yes. It looks like a black hole has opened up behind the button. It creates an extreme, harsh contrast ratio that our brains immediately flag as artificial, cheap, and just wrong.
To fix this, the source material offers a highly practical formula for calculating a realistic shadow. It advises taking the primary base color of the object, reducing the saturation by roughly 10 points, and dropping the brightness by roughly 20 points.
You are essentially taking the base color and mudding it down into the dark spectrum rather than resorting to a pure black overlay. It makes a world of difference.
And there is another mechanical adjustment the text recommends for realism, the spread value. It notes that using a negative spread value can eliminate shadow spillover.
This is a pro tip right here.
What exactly is the software doing when we adjust spread?
To understand spread, you have to understand the rendering sequence of a drop shadow. The software first duplicates the exact vector shape of your object. Then it offsets that duplicate based on your X and Y shadow coordinates. Next, it applies the blur algorithm to that duplicate. Finally, it renders this blurred shape underneath your original object.
Okay, so the spread parameter injects a step right before the blur. If I set a positive spread, the software takes that duplicate shape and mathematically expands its footprint outward before applying the blur.
Which results in a shadow that bleeds out heavily from all sides of the object. It creates a muddy, glowing halo effect that makes the object look like it is floating unnaturally high above the surface with a very diffuse light source directly behind it.
By using a negative spread value, I am commanding the software to shrink the footprint of the duplicate shape inward before blurring it.
Precisely. A negative spread tucks the core mass of the shadow tightly underneath the object. When the blur is applied, only the softest edges of the gradient peek out from the perimeter.
So it accurately simulates an object resting very closely on a flat surface under a strong directional light.
Yes, it grounds the object, giving it a dense, realistic physical mass.
This entire pursuit of realism brings us to a specific warning in the text regarding another type of shadow. The source explicitly states, modern UIs are using the shadows to build a visual hierarchy and layered structure. An inner shadow makes us think the object has a hole in it, which breaks the expected layering structure and can be confusing.
A very dangerous tool, the inner shadow.
Let's dissect this. Why is an inner shadow a cognitive hazard?
Well, it disrupts the fundamental mental model of modern digital environments, which is based on the z-axis. We have our x and y coordinates mapping the flat plane of the screen.
Right, horizontal and vertical.
Drop shadows introduce the z-axis, simulating depth pointing outward, up toward the user's face. The governing physical law of modern UI, often referred to as material design, is the stack of papers metaphor.
Okay, so the background of the app is the desk. A card is a sheet of paper resting on the desk. A button is a smaller scrap of paper resting on the card. Drop shadows validate this physics engine by proving that layer 3 sits above layer 2 and layer 2 sits above layer 1.
Exactly. The logic is universally additive. Everything stacks upward. An inner shadow, however, simulates a recess. When the shadow falls inside the boundary of the object, the visual cortex interprets it as a depression, a divot, or a hole stamped downward into the material.
So if a user is navigating an interface where every interactive element is presented as a tactile card floating slightly above the surface, and they suddenly encounter a text field with a heavy inner shadow, the physics engine breaks.
It shatters.
The text field looks like a hole punched completely through the desk.
It creates cognitive dissonance. The brain has to pause, even for just a few milliseconds, to reconcile the contradictory physical properties of the space.
And in an environment designed for frictionless interaction, those milliseconds of confusion are toxic.
Absolutely. Yeah. Unless you are intentionally designing a skeuomorphic interface that mimics complex mechanical hardware, like a recessed physical toggle switch on a synthesizer app, inner shadows completely violate the established dimensional logic of the platform.
Okay, so we use drop shadows to separate an object from its background, pushing it forward on the z-axis. But what if we want to manipulate the background itself to create an illusion of depth?
Now we're talking about blurs.
Yes, this transitions us perfectly into our final concept, blurs, and specifically the smoked glass effect. The text points out Gaussian blur as the standard tool, noting it extends the effect in every direction evenly based on the radius.
Gaussian blur is a mathematical powerhouse. It utilizes a convolution matrix, basically a mathematical grid that passes over every single pixel in the image. For a given pixel, the algorithm analyzes the color values of all surrounding pixels within a defined radius, calculates a weighted average based on a bell curve, and assigns that new blended color to the central pixel.
Wow. So it is systematically destroying high-frequency data sharp edges and high-contrast lines while preserving the low-frequency color data. It is the exact digital equivalent of pushing a physical camera lens out of focus.
That's a great comparison.
But the text elevates this from a simple visual filter to a structural layout tool when it introduces background blur. It states, background blur became popular when Apple started using it in their OS to achieve that behind smoked glass effect. An object with this effect applied blurs everything under it.
This was a seismic shift in how we handle visual hierarchy. Traditional Gaussian blur is applied to an object itself. You blur a photo to make it fuzzy. Background blur, however, turns the object into a dynamic, real-time lens.
A lens. Okay, explain how the software does that.
The rendering engine isolates the x and y coordinates of your vector rectangle, looks at all the layers positioned behind it on the z-axis, runs the convolution matrix over that specific intersection of pixels, and renders the blurred result inside your rectangle.
I always think of it as installing a pane of frosted bathroom window glass inside the app.
Oh, that's exactly what it looks like.
You know something is behind it. You can see the shapes and colors moving behind the glass. If a bright red icon strolls behind the frosted pane, you see a diffuse red bloom. So the context is preserved. You know you haven't been teleported to a totally different app. But the sharp details, the text, the sharp borders, they are mathematically obliterated.
And that obliteration serves a critical physiological function. It is a tool for hacking the user's cognitive load and managing foveal vision.
Foveal vision.
Yeah. Human foveal vision, the tiny central area of our retina where we actually perceive sharp detail, is extremely narrow. We rely on peripheral vision for context and spatial awareness, but peripheral vision is highly susceptible to distraction from high contrast movement.
Okay, so if a user is deep inside a complex dashboard and an alert modal pops up in the center of the screen, the sharp, high-contrast data of the dashboard behind the modal is competing fiercely for the visual cortex's attention.
Exactly. The brain is trying to read the alert, but peripheral vision keeps pulling focus back to the sharp grid lines in the background. It is exhausting visual noise.
I've totally felt that using badly designed sites.
Right. Now, in the past, designers solved this by throwing a solid, black, semi-transparent overlay behind the modal to dim the background. It worked, but it felt claustrophobic and often broke the spatial context.
Background blur solves the physiological problem elegantly.
Beautifully. By destroying the high-frequency detail of the background via the smoked glass effect, you instantly neutralize the peripheral distraction. The brain immediately recognizes the blurred area as out-of-focus background noise and effortlessly shifts 100% of its cognitive processing power to the sharp text on the modal layer.
It forces a physiological depth of field. It tells the user's brain exactly what matters in that millisecond without permanently erasing where they are in the application. It is the perfect marriage of complex mathematics and human psychology.
It really is.
Now, the source material also notes a brilliant, almost rogue application of blurs before we wrap up. It suggests that blurring can help generate non-standard point shadows by blurring an ellipse and placing it under the object casting the shadow.
That is a wonderful advanced technique that breaks free from the automated constraints of the standard drop shadow tool.
How so?
A standard drop shadow calculates a uniform offset. But in reality, if an object is lit from directly above, the shadow isn't a perfect offset. It pulls intensely right where the object touches the ground.
So instead of relying on the layout engine's automatic shadow algorithm, the designer manually draws a tight, dark ellipse, applies a massive Gaussian blur to soften it into an ambient gradient, and tucks it on the z-axis directly beneath the button.
Yes, it creates a bespoke contact shadow. It grounds the element with incredible realism.
And we are right back to where we started. We are just moving mathematically defined rectangles and ellipses around.
Every single complex, breathing, tactile interface is constructed from these exact atomic units.
We have really dismantled the illusion today. We started with the jarring premise that UI design is moving rectangles around, and I think we have proven it to be the literal mechanical truth of the medium. We unpacked the scalable math of Bezier vectors and the hardware efficiency that makes the rectangle king.
We examined the rigid physics of the box model, balancing the internal pressure of padding against the external repelling force of margins, all locked inside an invisible bounding box.
We traced the origins of the XY coordinate system back to the sweep of a CRT electron beam. We discussed the destructive math of flattening rotational angles. We explored the evolutionary psychology that makes a 4-point border radius feel safe, and how a centered border can secretly destroy your layout math.
We dissected the physics of light bouncing, proving why pure black shadows violate reality and why inner shadows break the additive z-axis logic of modern interfaces.
And finally, we looked at the convolution matrices behind background blurs, revealing how smoked glass is actually a sophisticated hack for managing human foveal vision and cognitive load. It is just a stunning amount of mechanical engineering hiding behind a sheet of glass.
It is an architecture of pure mathematics designed to simulate humanity.
This has been an incredible teardown. Now, before we sign off, I need to make sure you, the listener, have access to the actual blueprint we used today. Everything we dissected comes straight from Chapter 09, Objects of the book Design User Interface. If you are building a career in this space, this is absolute required reading. The book link is hype4academy.gumroad.com/l/ebook. That's HAIITAPE. The number 4 academy.gumroad.com/l/ebook.
Highly recommend grabbing it.
You can buy the book right now by scanning the QR code of the book link provided in the description below. And while you are down there, I have an explicit request. Please follow our show. We are dedicated to providing these intense technical design breakdowns and career-building content, and following ensures you don't miss the next teardown.
To close out today's deep dive, I want to leave you with a problem to solve.
Uh-oh, homework.
Just something to think about. We've spent this entire session proving the absolute unyielding dominance of the 2D rectangular box. The padding, the margins, the X and Y CRT coordinates the entire physics engine of our digital world is locked to a flat glass plane.
The ultimate 2D canvas.
But look at where the hardware is moving. We are entering the era of spatial computing. Mixed reality and AR headsets are removing the glass constraints entirely. The interface is no longer a phone screen in your palm. It is the physical volumetric space of your living room. The z-axis is no longer an illusion created by a drop shadow. It is physical depth you can actually walk through.
Wow. So what happens to the math?
Exactly.
Yeah.
When the canvas shifts from a 2D plane to a 3D volume, does the box model survive? How do you calculate padding when the container is the sphere floating in a room? Does the rectangle still reign supreme when the interface wraps around your physical environment? Or are we about to witness the invention of an entirely new geometry of design?
That is a staggering architectural challenge. Does the invisible rectangle hold up in 3 dimensions? We'll leave that for you to ponder. Thanks for taking the deep dive.